Good evening, everyone. My name is Carl Dobman, and I'm the Dean of the College of Architecture and Design. Thank you for joining us tonight, and also welcome to everyone that's joining us online this evening. The College of Architecture and Design at Lawrence Technological University offers degrees in design disciplines from things that could fit in your hand all the way up to the scale of the city. There's an incredible range of scales in our work. As a technological university, it's also often the technology that operates as a bridge between these ranging scales and diversity of the disciplines. I'm incredibly excited to welcome Virginia with us tonight. Her work is at the intersection of design, technology, sustainability, making, and material science. Her work is poetic, polemical, and beautiful. You'll see Virginia's dexterity in moving between scales and disciplines this evening, and her work represents a new model of practice that, right? I thought you chuckled. A new model of practice that does not rely on existing routines, but instead their firm develops their own tools, software, and their own materials. Virginia Fretello is an architect, artist, and educator. She's a partner in the award-winning design firm Royal Fretello, and is a co-founder of the startup of the company Emerging Objects. Virginia recently won the International Interior Design Educator of the Year award, and their firm, with her partner Ron Royal, was selected as part of Emerging Voices from the Architectural League of New York. Virginia is an associate professor at San Jose State University. She holds a Master's of Architecture degree from Columbia. She's taught at SCI-Arc, Clemson, and Berkeley. Her research has been funded by the EPA. It's been published in Interior Design Magazine, the New York Times, and Wired Magazine, to name only a few, as there's a long list of places where their work is showing up. Their work has been recognized by several institutions, including MoMA and the Cooper Hewitt. So maybe I'll leave it at that. I was going to tell embarrassing stories, but maybe we can do that later. So let's welcome Virginia to share her work with us tonight. Welcome.
Thank you so much, Carl. Thank you for that kind introduction. Thank you all for coming. I'm delighted to have the opportunity to share the work and the research of Emerging Objects with you this evening. I decided to call this lecture Crafting the Future because I'm part of a startup company called Emerging Objects, where we develop materials and applications for 3D printing. And we see 3D printing as a possible, viable, and inevitable method of manufacturing for the future. And so I just want to talk about how some aspects of 3D printing can be used in architecture and interior design and art as well, and focus on concepts such as on-demand, printing and making buildings on demand, mass customization and democratic design, no waste, and material innovation. On demand, make only what you need. With a 3D printer, you can store files, products, buildings, building components in a computer until they're needed. And then you can print on demand. This eliminates surplus. It also allows you to print on site. So you can ship a digital file around the world instead of shipping a product or a component around the world. So in theory, I could design something in San Francisco, I could send it to a printer in New York, it could be printed and installed there. And I don't have to ship a light fixture across the country. And this reduces the carbon footprint that we as architects and designers are contributing to. So here's an example of something that was designed in my studio and assembled by someone else across the country. And this is the Starlight. It's made out of 3D printed cement, a material that we invented, which I'll talk about a little bit later. And one of the nice things about this particular light fixture is that not only can the digital file be sent across the world, and each of these parts can be printed somewhere else, they're small. They're the size of your hand. So someone can very easily assemble these small parts. And this same light fixture can be 3D printed out of different materials. So here on the left, you see copper infused filament, and on the right, white bioplastic, which is made out of corn. Another advantage of 3D printing is that it allows for mass customization. You can design for specificity. So here in the design of this curtain, you can see, if you look at the drawings on the left, every one of these elliptical forms is a different profile and a different depth. And the narrower, deeper tubes are located at the top of the window, and that masks the summer sun from coming into the interior. And the larger, shorter tubes are at the bottom of the window, and that allows the winter sun, the low winter sun, to come in. So because every one of these tubes is unique, I have a customized surface that responds to the solar orientation and the geography of the building. But it still allows me to have views out into the landscape beyond. So unlike a traditional curtain or screen that's veiling the interior, I can see downtown Oakland. Again, designing for mass customization with specificity. Unique, one-of-a-kind building components can be generated quickly and economically from advanced three-dimensional modeling software. This bench, for example, is composed of 300 unique 3D printed parts. It's inspired by the seat slug, a biomorphic interpretation of a bench. The form comes from Flabellina godardi, the newest species of sea slug discovered off the coast of California, and by the infinite tessellations of Japanese karakusa patterns. So those patterns are repeated across the doubly curved surface of the bench. And you can see here the 3D printed parts that come out of the printer in their green state. And you see that every one of them is unique. All of these parts are finished and have a glossy coating on them so that they reflect the sunlight. This bench was intended to be outside. And they're assembled here together, again, as bricks or blocks or tiles that fit into your hand to make this 11-foot long 3D printed bench where every tile is unique. So the seat slug demonstrates the potential for mass customizing, because 3D printers don't care. They don't care if they're printing 1,000 of the same parts or 1,000 unique parts. The cost of the material is the same, and the labor needed to make each part is the same. Custom parts can be manufactured without additional costs. Now, we can design for specificity, but we can also customize for variation. In addition to powder-based printing, which you saw earlier, we're exploring paste extrusion 3D printing, and it's allowed us to explore radical 3D printing techniques, resulting in the development of a series of objects called G-code clay. Typically, extrusion-based 3D printed ceramic objects are defined by the layers of clay, whose striations are present on the surface of the 3D printed object. But as demonstrated here, the surface quality takes on the appearance of a knitted textile. The clay is looped, purled, and knotted as it droops away from the surface. And occasionally, there's a dropped stitch, which causes a loop to pull away and make every single print unique. The objects that are fabricated use various clay bodies. Sometimes we use recycled clay from the ceramics department at Berkeley. We use B-mix with grog. We use paper clay. We've used porcelain and other local clays that we've actually dug up in front of the architecture school. This exploration doesn't concern itself so much with the shape or the profile of the object, but rather the path that defines the movement of the 3D printer. And through this exploration, the printer is pushed outside the boundaries of what would typically define the printed object. And we've created a series of controlled errors that create new expressions in clay, defined by the plasticity of the material, gravity, and machine behavior. The objects formed through this process have the potential to serve as enclosures for light and for life, such as plants and water. But we're working towards the creation of building-size enclosures that have distinct qualities of earthiness and furriness or softness, enclosures that have textures that can enhance functions. For example, the texture on this mud dwelling in Africa serves as steps and speaks to the frequency with which the surface needs to be replastered. And so we're working with an engineer to develop a high-speed, large-scale 3D printer, specifically for 3D printing clay and earth to make room-sized structures. Democratic design. Anyone can do it. You can do this too. You don't need a special, expensive 3D printer. Desktop printers sell for as little as $130 now, and you can buy one and have it on your desk in studio. You can use inexpensive ecological materials such as PLA or polylactic acid or bioplastic, which is made out of corn. And you can 3D print your own building components. This is a block we call the Pico Roco block. It's a modular 3D printed object for wall fabrication, and it's shown here printed in translucent orange bioplastic. The wall behind the model here is composed of blocks with a dimension of 5.75 inches by 5.75 inches by 2 inches, so that it fits on the build bed of a small desktop printer. 3 different blocks are used in the construction of the wall, a 2, 3, and 4-hole block. And each block can be randomly rotated to create the variable pattern found in the surface of the wall. The blocks are held in place with 3D printed orange clips that have 4 prongs that connect the blocks at the corners. The wall takes advantage of the translucency of the bioplastic, giving it a softly scalloped, diaphanous quality when used as an enclosure in front of a window or a light. And one of the nicest aspects of this process is that it doesn't require skilled labor for assembly. Anyone can assemble their own objects and make customized enclosures. So these desktop printers have addressed the contemporary concerns around accessibility and custom manufacturing. 3D printing a custom enclosure is not a future proposition, it's a current reality. So building on the knowledge that we gained making the Pico Roco wall, Emerging Objects fabricated one of the largest PLA or bioplastic-based 3D printed structures built to date. It's called the Star Lounge. It's a unique form, and it's different from many of the other 3D printed structures that you've seen around the world because it demonstrates the architectural potential of using a farm of small, inexpensive desktop printers in order to 3D print a building. The freestanding dome is 8.5 feet tall with a footprint that measures approximately 11 by 11 feet. The dome is composed of 3,000 hexagonal blocks printed in various translucent colors that correspond to a particular block type, which helps simplify the construction process and creates a beautiful and logical pattern of stars and hexagons that comprise the 21 larger panels which are riveted together. The patterning of the Star Lounge is inspired by cut tile Arabic star motifs and mid-19th century American quilts. Ironically, the use of stars is prevalent in both of these traditional Muslim and American genres. The hexagonal blocks that make up the Star Lounge, the stars and hexagonal panels, were printed using a bot farm of over 100 3D printers. This is the future of production. Anyone can have access to a bank of printers in his or her office, home, manufacturing facility, or school. And this is how the future can be produced. So to facilitate file management, because we designed this again in California, and we sent the files to New York to be 3D printed, we designed the structure to have only 28 unique block types instead of 3,000 unique block types, because we didn't want to send 3,000 digital files to the manufacturer. So these 28 unique block types make up the doubly curved dome surface, and each block has a number printed on the interior of the surface to locate the block in the assembly. The design of the dome structure maximizes the efficiency of the printer and the print volume. 2 blocks could be printed per printer without support material in just over 1 hour. The Star Lounge demonstrates that prefabricating small-scale, hand-sized, and efficiently designed 3D printed parts for architectural assembly is feasible. It's cost-effective, and it opens the door to creating 3D printed bricks, tiles, walls, ceilings, partitions, and cladding, sustainable buildings of the future. No waste. With 3D printing, because it's an additive manufacturing technology, there is no waste, like subtractive manufacturing, where you're cutting or milling away material to make an object. So if you see the image here on the left, this is a planer where someone's planed down a lot of wood, and you see all the residual sawdust. This is a material that is a byproduct of manufacturing, and subtractive manufacturing in particular. And we don't see this because in your wood shop here, I'm sure you have a wonderful vacuum system that takes all of that dust away. Okay, so you have some raw material to work with here. In the image on the upper right, I've taken the sawdust and put it into a powder printer. And we are able to print with this material. So because additive manufacturing makes no waste, I can continually recycle that recycled material in the 3D printer. And of course, the video on the bottom is just to familiarize you with powder-based 3D printing if you're not familiar with this process. There's essentially a build bed on the right and a supply bed on the left. And that supply bed is filled with the material, in this case, a plaster-based material, that raises up and spreads a thin layer across the build bed. And then an HP inkjet head sprays a binder onto a very thin cross-section of the digital model. That build bed drops down, the supply bed comes up and spreads another thin layer. And that happens hundreds or thousands of times until a three-dimensional object is made. It's then excavated from the loose powder, much like an archaeological dig. So sawdust. 7.1 million tons of wood waste are generated in the United States every year. And of this, 67%, or 6.3 million tons, is potentially recoverable. And so we wanted to discover if we could recover this waste material to create a 3D printable wood material. And we did. So we've developed a formula for 3D printing with wood waste. It's sawdust that is then pulverized into a flour. And one of the beautiful things that emerged through this research is that there's a new kind of wood grain emerging here that's based on the orientation of the object in the 3D printer. So we can control that wood grain based on how we position the digital model in the printer. It's translucent when you print it thinly enough. And we've experimented with different types of wood. So this is a soft wood, it's pine. This is maple. And this tile is made out of walnut shells. And that tile is designed again using the Karakusa pattern to repeat across a surface continually and be rotated to hide the seams to make a much larger pattern. One that has pores in it that allows for the passage of light and views and air. So no waste, and we've touched on material innovation. material innovation, there's more, okay? So through material innovation at Emerging Objects, we're able to address one of the world's most pressing issues today, the impact of production, consumption, and the disposal of goods upon the Earth's resources. We want to invent materials that are sustainable, durable, and affordable, that can be used to craft and construct new objects for the built environment. So to emphasize this point, I just want to tell you a little short story. This is a very simple object. This is a very humble teapot that was manufactured by Friesland Porcelain and sold by the Melita Group in Germany in the 1970s. The teapot was purchased in Salt Lake City at the Zion's Cooperative Mercantile Institution. This was the first department store in the United States by a woman named Sandra Newell. For his work, her husband, Martin Newell, needed a simple mathematical model of a familiar object. So Sandra suggested modeling their tea service since they were sitting down to tea at the time. So Martin sketched the teapot freehand using graph paper and a pencil. And following that, he went back to the computer laboratory and edited the Bezier control points on a Tektronix storage tube, which I don't even know what that is. This is like so long ago. Again, he did this by hand. So starting from these and with some algorithms, he created a mathematical model for the teapot. It turned out that the teapot was the ideal object for the graphics experiment of the time. It was round, it contained saddle points, it could project a shadow on itself, and could be displayed accurately without a surface texture. So Newell made the mathematical data that described the teapot's geometry publicly available. And soon after, other researchers began to use the same data for their computer graphics experiments. And the teapot quickly became a beloved staple of the graphics and computer community. Teapot after teapot graced the pages and covers of computer graphic journals. Anyone with a new idea about rendering and lighting would announce it first by trying it out on the teapot. It's been rendered as if made of alabaster, red brick, leopard skin, and animal fur. And most famously, in 1987, a paper introduced the image, casually describing it as one of the 5 Platonic solids, plus the newly discovered teapotahedron. Although technical progress has meant that the act of rendering the teapot is no longer the challenge it was in 1975, the teapot continues to be used as a reference object for increasingly advanced graphic techniques. In fact, with the advent of the first computer-generated short films and preceding full-length feature films, it's become popular to include the teapot in one of the film's scenes. Here in the movie Toy Story, the Utah teapot appears in a short tea party scene. It's also appeared in The Simpsons, Monsters, Beauty and the Beast, and many, many other movies. Now the Utah teapot has finally come full circle. It's no longer just a computer model based on an actual model. It's now an actual teapot based on a digital model. It's widely available in many renderings in different materials, from small plastic knickknacks to fully functional ceramic teapots. It's sometimes intentionally rendered as a blocky, low-poly object to celebrate its origin as a computer model. And in 2009, the Belgian design studio Unfold 3D printed the Utah teapot in ceramic with the objective of returning this iconographic object to its roots as a piece of functional dishware while showing its status as an icon of the digital world. And in 2015, Emerging Objects followed suit. But this time, we printed the teapot out of tea. Through material innovation and 3D printing, we're able to make physical, new objects, and the objects we make are intended to engage all of the senses, as well as possess extraordinary geometric complexity. Our process raises important questions about the historical and contextual meaning of objects. And when such questions are asked of objects, we believe it leads to creativity and speculation. We're also interested in responding to contemporary concerns, such as the impact of production, consumption, and disposal of goods. So the tea is a material that has the ability to be transformed through the budding technology of 3D printing. The production and consumption of materials like tea and coffee offer many opportunities to harvest waste. So tea leaves and stalks from the field, tea fluff from factory floors, and used tea leaves are all suitable materials for 3D printing. And because we printed the Utah Teapot, we decided to make teacups as well. And if you have teapots and teacups, you have to have teaspoons, right? Quite literally, the spoons that are printed here are printed in tea, and they are exactly 1 teaspoon by volume, 5 cubic centimeters. Other materials, such as coffee grounds and coffee flour, have the ability to be transformed through the technology of 3D printing. The production and consumption of coffee offers many opportunities to harvest waste. Starting in the field where the coffee beans are picked, one finds the first opportunity. The coffee beans can be found at the center of the coffee tree's fruit, or coffee cherry, as it's called. The coffee bean goes through a process of drying and washing as it is separated from the cherry's pulp and outer skin. The bean continues on its path to roasting, but the cherry becomes a waste product of coffee. It often gets dumped in the rivers or left to rot in heaps. Coffee flour, however, is a new product that's being made by collecting, drying, and pulverizing those same cherries into a powder that is certainly edible, but also has excellent 3D printing capabilities, as evidenced here in these flavorful and aromatic 3D printed coffee cups. Materials such as sugar can also easily be 3D printed, and because of sugar's inherent solubility and stickiness, it's possible to print the sweetest of confections. In this case, sugar spoons are printed in volumes corresponding to 1 teaspoon, 2 teaspoons, 1 tablespoon, and beyond, and these printed sugar spoons can be stirred down and dissolved into one's coffee to flavor it with sweetness. Another material we've been experimenting with, Chardonnay. Pumice is the solid remains of grapes after pressing the fruit to make wine. It contains the skins, pulp, seeds, and stems of the fruit. Grape pumice has traditionally been used to produce brandies such as grappa, which the Italians have done for thousands of years. But today in the United States, pumice is mostly used as fodder and fertilizer. But much like the coffee cherry, grape skins and seeds also have the potential to be dried and ground into fine powders for 3D printing. So we've used Chardonnay pumice to make wine goblets and Chardonnay building blocks, which we radial arrayed to make an ice bucket for Pierre Jouet. But perhaps one of the most frequently used materials in our studio is salt, because we are in the Bay Area, so it's a local material for us. It's been industrially harvested from the Bay for over 150 years. At its peak, the Bay had 40,000 acres of land dedicated to salt production and produced over 1.3 million tons of salt annually. It's a renewable resource, it's incredibly inexpensive, and it's made simply through evaporation. The Solar Salt Works in the San Francisco Bay uses only natural power from the sun and the wind to make this material. It can be printed and formed into objects that we're familiar with, such as functional salt shakers. Salt always has incredibly beautiful optical properties of translucency, no matter how thick or thin it's printed. We've experimented with shaping the salt blocks into forms that would otherwise be impossible to make with molds. And we've experimented with techniques for interlocking, stacking these 3D printed salt blocks, and have explored the structural properties of the material as well. The micronized salts we print with have an ultra-fine resolution and can be printed very thinly with very, very fine details. Each fall in the Bay Area, 150,000 tons of salt is harvested. So this is last year's harvest at the beginning of the harvest. So it's a pretty amazing sight to see. The company that owns the crystallizers in the Bay has given or sold 16,500 acres of land to the government for wildlife redevelopment, and an additional 1,400 acres has been set aside for a residential development of 12,000 homes for 30,000 people, which raises the question, does salt have the potential to be an integral material resource for this housing development should it happen? So we decided to create a salty glue, kind of igloo, made out of salts and glue, to see if we could harvest this material from the ground beneath our feet. And we were inspired by the forms we found in traditional salt extraction processes and designed an igloo that could be 3D printed with the salt from the San Francisco Bay. We designed and printed individual tiles that had crystalline forms inspired by the microscopic forms that you find inherently in salt crystals. And we created an enclosure made out of salt. The salt is intended to preserve and enhance the role of the interior environment. It allows diffuse light to enter into the interior. And from the exterior, one can see glimpses of the interior. We always imagined the salty glue would be used in the interior to create semi-private enclosures, to envelop spaces such as dining rooms where this material connection seemed logical and meaningful, or maybe a bedroom that could be enhanced by the softening of light. The salty glues are objects in the interior. They serve as vessels for human activity. Rubber. This is another material that we've experimented with. Automobile tires are one of the planet's biggest waste problems. In the United States alone, 290 million scrap tires are disposed of every year. Around 80% of those tires are recycled, but we'd like to find a new application for the rest, which is 60 million tires still. In fact, the world's largest tire graveyard in Kuwait, is so vast that it contains over 7 million tires and is visible from outer space. Worldwide, there are almost 1 billion tires discarded annually. Discarded tires are so problematic because of the large amount of tires produced each year, their inability to degrade, and the fact that they contain a number of components that are environmentally damaging, such as carbon black. So we've been working with a company that's developed a material called MRP, micronized rubber powder, and it's generated through a cryogenic manufacturing process. The tires are frozen, reduced to a rubber crumb, and then ground into a really fine mesh that might typically be used in roofing or in asphalt pavement. The rubber powder is incredibly inert, and therefore it's mixed with other additives to make it printed. And the mixture is adhered together with an organic binder. Recycled rubber tires are often used to make very refined building products such as floor tiles, carpet padding, roofing tiles, and waterproof membranes. But using MRP, we're able to turn this waste material into new objects. And we imagine new products emerging as well, such as furniture for the interior or possibly for playgrounds in the landscape. Cement. Cement is the most ubiquitous building material in the world, and it needs to be transformed for 3D printing. According to the United Nations Environment Program, in 2012 alone, the world used enough concrete to build a wall 89 feet high and 89 feet wide around the equator. From 2011 to 2013, China used more cement than the United States used in the entire 20th century. It's estimated that 10 billion tons of concrete are produced worldwide each year, which translates to 2 tons of concrete per person in the United States. So this means unrivaled amounts of natural resources are being depleted annually just to produce concrete. Of equal concern is the issue that the production of Portland cement releases enormous quantities of carbon dioxide into the atmosphere. And 1 billion cubic meters of water are used each year in the production of concrete as well, demanding an urgent call for concrete design and production to become more ecologically responsive in the 21st century, as the planet cannot continue to consume concrete at our current rate. One of the advantages of 3D printing with concrete is that no formwork is required. Oftentimes, formwork can cost up to 60% of the total construction cost. Very, very little water is required for 3D printing with concrete, and a printer can run on a single 110 outlet, reducing energy consumption as well. Emerging Objects fiber-reinforced cement polymer for 3D printing expands cement's capabilities, as no formwork is required. It allows for file-to-fabrication process, and it has structural capabilities. Our fiber-reinforced cement polymer has a compressive strength of 4,700 psi, compared to typical concrete, which has a compressive strength of 3,000 psi. And it's translucent. So we've experimented with aggregating these 3D printed concrete tiles to create larger objects. We've experimented with different methods of attachment. This slide shows an early method of fastening using binder clips. We've experimented with different finishes, so glossy, which you saw on the seat slug at the beginning of the lecture, matte here, which has been sandblasted to bring out the grain of the 3D printed cement. These tiles, 20 hexagons and 12 pentagons, are assembled together to make the P-ball, a puffy spheroid or a buckyball, in which each tile is unique and has a specific geometry that allows the parts to come together to make a more complex whole. And one of the most rewarding aspects of 3D printing for me is that the digital model used to make a scale study model is the same digital model that can be used to print something at full scale. So Bloom is an experimental pavilion that explores 3D printed Portland cement at an architectural scale. It's 9 feet tall with a footprint that measures 12 feet by 12 feet, and it's composed of 840 customized 3D printed cement blocks. The floral motif embedded in the surface of Bloom is derived from traditional Thai flower patterns, and it's mapped cylindrically onto the surface of the structure. This creates a figural pattern comprised of openings in the surface that produce stunning visual effects of light, shade, and shadow on the exterior and the interior. On the interior, one can find an internal structural grid that carries the forces of the weight of the cement block down to the ground. The individual blocks were printed on a print farm of 11 powder printers with a special cement composite formulation comprised of iron oxide-free Portland cement. Iron oxide imparts a gray color to cement, and its removal makes these blocks much, much lighter in color. And if you look closely, you can see the holes that are printed into the sides of the blocks, and that's how the blocks are fastened together. The blocks at the bottom of the wall are about 5 inches deep, as you can see in the drawing here on the left in the floor plan, and the blocks at the top of the wall are about 1 inch deep to reduce the weight of the blocks as the load is transferred down. The curvilinear form of the overall structure adds stiffness to the thin, lightweight shell. In plan, Bloom is a curved cruciform that rises 9 feet to meet the same shape that's rotated 45 degrees, creating a torqued X, with an entrance 45 degrees off its primary axis. All of the blocks are enumerated to designate their position in the overall structure. And they've been assembled into 16 large, lightweight, prefabricated panels, which can be put together in just a few hours to create an enclosure. So this quick video just shows how quickly the pieces come together and how it can be set up and dismantled. It's been shipped around the world in these large pieces, and they're also very lightweight. So there's a lot of air and porosity in these 3D prints, which reduces the mass. Okay, so now it's time to wake up a little. Okay, so we're going to talk about bad ombres and switch gears. So ombres that are simply bad are because they don't transition from light to dark or from one material to another seamlessly, because they're abrupt, they're harsh, they're unnatural, they're out of place, they're artificial affronts. So when Donald Trump said he wanted to build a wall to keep out the bad hombres, he was referring to bad men. But what he said was bad hombres, which is something entirely different and something that a wall, a distinct line, or a boundary creates. Oops. An ombre allows for unbroken transitions across borders and between landscapes. It crosses political boundaries fluidly and allows for continuous cultural connections to be made. So in response to Donald Trump's bad hombres statement, we've created a collection of 3D printed objects in clay. The objects smoothly transition from one material to another seamlessly, and the clays come from all over the world to California, where they're combined in a single tube that extrudes clay continuously. Using G-code, the computer language that speaks to the printer, we take the clay on a walk along a path. The whitest clays are porcelain from the Matari Bay in New Zealand, where the porcelain is translucent and resonant. The dark black mountain clays come from the pits of the South in the United States, and these clays are mixed in California to create a custom recipe that makes a new, stronger body. Through the use of varying clays, the bad hombres are intended to create new geographic and geologic landscapes. They're objects that transcend borders. They're simultaneously rooted in the ground from which they emerge, yet they're global and delusive. No object in this collection will ever be recreated exactly the same way again. Failure, individuality, distinct character, unique markings are all what make these pieces special. Their differences make them one of a kind, but the ombre itself ties them together. So we've been pursuing continually this idea of ombre and decided to introduce it to the powder materials as well. And we wondered, would it be possible to move seamlessly from one material to another? And how does that enhance our understanding or perception of material, color, or culture in objects? So to begin this research of creating material ombres using the powder-based 3D printing, we started with Chardonnay and cement. Cement, of course, being the most ubiquitous building material we could find, and the Chardonnay being an abundant local material for us in the Bay Area, as it comes from close by Sonoma. So we printed tiles out of cement and Chardonnay, and we also mixed the cement and Chardonnay together. And this gave us a large surface, but there were still joints in the material, which pushed me to develop a formula for printing with Chardonnay and cement, one that would allow for the smooth transition from an architectural and agricultural material to a geological material without any joints, adhesives, or mechanical fasteners. So it's now possible in a formally complex 3D print to move seamlessly from a full-body Chardonnay to a more subtle tint finish with a pale, crisp cement. And I realized that depending on how the supply bed of the 3D printer is filled, one could control that material ombre. The ombre decanters shown here demonstrate a gradation from the Chardonnay to the cement. The forms of these decanters are inspired by ancient ceramic wine carafes and amphora, and the surface textures are inspired by the diamond pressed texture frequently found in objects such as wine glasses and decanters. An attempt to create a new color provoked me to test 3D printed curry with cement. So the object shown here is printed in a combination of curry and cement, both customized recipes using off-the-shelf materials that demonstrate the ease of creating evocative multisensorial objects. The aroma of the curry as it's being printed is pervasive. It fills the room. This object is now 8 months old and it still is fragrant. And finally, what's next? A 3DP cabin. So we're trying to bring all of these materials and technologies together to build a building made out of 3D printed components. This diagram just illustrates how we're bringing together 3D printed ceramic tiles on the exterior, 3D printed bioplastic tiles on the interior, Chardonnay and cement tiles on the front and back facade. And we're about 75% of the way finished. So here you can see the 4,000 ceramic tiles that are cladding the roof and the exterior walls, the bioplastic panels that make up the interior. The panels are translucent. They have color-changing LED lights behind them, and they change color with the light as well. And here, of course, are the Chardonnay and cement planter tiles that will hold vegetation. The building is located in a garden. And it's our goal to make everything using this technology and the materials that we've been experimenting with. So we're printing and designing our own furniture, such as chairs. We're designing the tables, the tabletop accessories, and even the hardware, with the intention of creating a total work of 3D printed architecture, interior, and art. One that uses innovative materials, has no waste, can be manufactured on demand, and printed by anyone, even you. Thank you. So I'm happy to answer any questions, if there are any. Okay.
I noticed on your website you had a heading for chocolate. And I went through it and there wasn't anything there. I was wondering what you're doing with chocolate.
Oh, there should be some little chocolate bunnies there. So this was several years ago when we were experimenting with the sugar and combining that with cocoa, using the powder printing to print chocolate. And that was one of the early aromatics or food-based printing experiments that we were pursuing. And it works quite well. Yeah. Yes?
You compared compressive strengths for the two cements. What about the tensile and shear strengths?
I don't know the answer off the top of my head. I don't remember. But we've worked with engineers at the University of California to do the stress, the strain, and the compressive strength testing. Yes.
Is there a specific type of material that you guys use to crush your actual materials that you find to get them so fine in order to mix them in? Or do you go through a whole process?
No, we buy most of the materials. They come in the state that they're in. So like the salt, for example, I pick up on my way home from work from a company called Salt Unlimited. And they have many different grain sizes, and I don't use their finest because I would have to buy a pallet of that, but I use like their second finest. The wood flour is essentially free, and we just have to pay for shipping because no one wants it. some of the materials, like the coffee grounds and tea grounds, I grind up myself, and I just use a coffee bean mill. Yeah. Yes.
For like the sugar spoons that you said could be. For the sugar spoons that you said could be used like in the coffee, like there's no like additive glue or anything that's unsanitary that you couldn't do that with.
So the binder that we use is edible. It's mostly water and with a little bit of alcohol. So I could print. Yes, I could print with vodka. I could add some more flavoring to that for you. Yeah. Yeah. Yes.
Going back to the salt tiles, what do you use to waterproof them or weatherproof?
We polymerize all of the powder-based prints. So the binder is the water and alcohol-based solution, and when they come out of the printer, which I showed in the video, they're a little bit brittle still, so we either dip or brush a polymer on them to strengthen them.
So for plastic, for example, plastic, when you print, there's like some shrinkage to it. So did this sort of like occur with other materials? Did you notice that it's like, what's the tolerance for printing? Or is there like, is it noticeable? Like,
It varies from material to material. So like the cement is incredibly precise, as you saw in that bench. Those pieces just go together perfectly. And if we had a climate-controlled laboratory, they would probably be even more perfect. But we don't. We're in California, and the windows are open all the time. Materials like the Chardonnay, it shrinks a little bit, and I think that the different woods, they still, even though they're all in powdered form, they still retain their own inherent material characteristics. So the pine is softer than the maple, and it's a little bit spongier when it comes out of the printer. The ceramic, of course, shrinks when it's fired up to about 22%, which you guys know this because you're doing it here.
I guess my next question is like, how does this affect the mass customization? Does it actually work in systems quite well because everything is actually like being affected at the same time, or does it actually create issues with the system?
So, I realize I've forgotten to show one project, but we have a project called the Cool Brick, and it's a 3D printed ceramic brick that has a lattice structure. And when it was fired in the kiln, of course, they all shrunk, and they don't fit together perfectly like they do in the digital model. And we just decided to compensate for that by using really thick mortar, just to combine high and low and say there are really traditional ways of dealing with tolerance, and we'll just take advantage of those. So it doesn't have to be perfect every time, and we accept that and can anticipate that.
So, sorry, one last
That's
question.
okay.
So does this kind of means that not really everybody can use it? It has to be sort of like a skilled labor to understand how to assemble with them. And you said everybody can sort of assemble and put it together.
I think those orange blocks were pretty able. That was a 4-year-old assembling the orange blocks. So all of the orange blocks are assembled just with a little clip, right? These tiles, for example, here, they have a J profile, so you just hang them. That's it. Anybody could do it. You just hang it on the building. So it's our goal to make these things using really simple hardware, or to design the shape in such a way that it's intuitive.
Thank you.
Thank you. Yes.
I appreciate the lecture. It's fantastic. The question I have is, a part of making the technology democratized is obviously allowing, as you say, anybody to be able to do it, a reasonable amount of skill. And I think one of the big hurdles for 3D printing I've discovered is obviously the scale. Right? So the scale of the printer dictates the component size that you're using, and I think one of the things that I like is how that component size hasn't really limited in terms of your overall scale of assembly, or even limited the formal qualities of the work. But my question comes out of that is that through admiration of that, I'm like, how big are these print farms? I mean, like one of these prints, I know, I mean, it's just hours and hours and hours, and I seem that there seems to be like thousands of these.
These?
So Like, but you know what I'm saying, like how,
Yeah.
like how many print farms do you have to make a building out of that many small thousands of components?
So,
Does that make sense?
yeah, but I mean, I think that's true for manufacturing at any
Right.
scale,
But I
right?
guess, but the point is like, at what point is it manufacturing
Uh-huh.
versus, say, mass customization or kind of democratized making?
But I don't think that
Okay.
manufacturing has to be mutually exclusive from mass customization, right?
Right.
Yeah.
But I guess for me, it's like a scale of time. It's a time factor, right? So like,
Yeah.
how many machines can you have running at once? Like, how many people have to run them?
Well, I think maybe as service providers, more and more service providers come on board, and right now we kind of only have Shapeways.
Right.
Like Shapeways could manufacture my PLA pavilion. It would cost me a lot of money. Or I could make it myself. You know, I have a printer in my kitchen underneath the microwave, and sometimes I just come home and press print, and I can do that every day, you know, and print all day. Yeah, I mean, we're still at maybe a boutique operation, right? So we're not manufacturing. And with this project, we're hoping to show that this is a reality. You can 3D print building components. You can use them in a hybrid system with conventional frame construction, for example. It's not that, oh, you have to have a whole 3D printed house, right? So it's a question of scale, yeah. But these 4,000 ceramic tiles, we printed, we stop and start, but we can print 100 tiles a day with 4 printers and 1 technician.
Yeah, that's kind of what I was looking for.
Yeah. Okay.
No, but I mean, I'm trying to like do the math in my head. Like,
Yeah.
how many printers would you need?
So we need one person to pack tubes and press print, and we get 100 tiles a day. Yeah. Yes.
So if you think of these in the project you didn't show us as masonry, okay, or as blocks, and you might densify them without being totally solid to make them stronger and able to handle more compressive forces. And you think of the shapes which are non-geodesic or non-geometric that we've used masonry to achieve, just with stone, without any tensile properties whatsoever. That was A. B is Jim was building something.
This is going to be a long question.
Where he got to the point where he says that he's scared himself. When he was working with his students, they were assembling this thing, and at some point he says, "Oh my God, this thing could fall down, like hurt somebody." So
That was out of wood, by the way.
yeah, it was wood. But I imagine that you could make these in any size you want, just like masonry, and make something really large that
Yeah.
wasn't geodesic. Have you tried that yet? Or are you thinking about it?
I was just talking about, I went to a lecture by Philippe Bloch, and he makes all of these amazing vault and dome-like structures, and he's looking back at Eladio Diestri and Canella and these amazing engineers that you're talking about. And he's also just this week releasing a new software that I think would allow someone like me to model something like that in the computer, without having to go to an engineer and say, oh, I'm not an engineer, and I can't say more than just intuitively where the forces are going to be. But yeah, so we could print every piece custom, and it would all come together and be held in place compressively.
What I want you to do is get an engineer and see how far you can take it. I think that's there.
It's hard because we've tried that, and our materials are not materials that they're familiar with. So my cement has, your cement is not like regular cement, so I don't know what forces it can resist. So what we end up doing, and this is a little bit crazy, we use this 3D modeling software that Pixar uses, and we animate it. We literally just drop the building on the ground in the computer, and if everything stays in place, because it has gravity and it has collision detection, you're like, okay, well, it'll probably work. But that only works at a certain scale of a pavilion, which of course is risk-free compared to something that lots of people are going to be walking under, right? Yeah. Yes?
I know you said you go through a polymer process to enhance the structure of the tiles. Have you found any degradation at all after that?
We've used different polymers, and so yes and no. So there's one that we pretty consistently use that's low VOC, it's clear, and that one we've been using since 2010, and it still looks good and it's still strong. We tried for a little while a polymer made out of recycled paper pulp, and in really humid environments, it just softens up completely. So we sent some pieces to Bangkok, which you can imagine, very different climate than California, and they just, and so we said, take it back inside, put it in the air conditioning. So yeah, the polymer, the strength of the polymer is really important. And we could use stronger polymers, but we're just not set up for that. So, yeah. Yes.
I guess sort of piggybacking on that, would then the teacup and coffee mug that you made be watertight where you could use them, or would they fall apart?
I could make them watertight for, yes, I could use a polymer that is food safe for liquids, yes. Yeah. Yes.
In the interest of sustainability for some of these works, what is, like, have you studied the embodied energy for some of these 3D printed pieces as compared to traditional building methods? Like the process of accommodating some of these new materials and powdering them and using the pre-3D printed farms, is there like a comparison?
I haven't done it myself. There was a PhD student at Berkeley who did some of that research, and he was looking at printing with plastic and metals and then salt. And in his study, because we weren't shipping salt around the world, ours was less energy intensive, obviously. But I think we're so early on in this technology that it will require the focus of either companies or researchers to do that work. It doesn't exist, I think, wholly and comprehensively yet. Yeah.
Sorry, last question from me. It's a trivial question. Your presentation was all formulated around sustainability. And so one question that came up to my mind, how long is the life expectancy for us, for the building, like the full building that is to be 3D printed out of components? Like,
Yeah, that's a great question. So these ceramic tiles, I fully expect to last 30,000 years, just like any other ceramic. The bioplastic tiles on the interior in a normal environment should last 100 years. So only if they were taken to a facility where they were intended to be composted and broken down under really high heat would they dissolve.
so like the changing climate won't really actually.
Not on those, no. And that's one of the reasons why this building is made with these materials. The weakest link will be the Chardonnay tiles, but we'll see. There's no way for me to predict the future, right? I just have to do it. Yeah.
So I'd like to thank you, Virginia. I mean, with a lot of this technology, I think there's a lot of discussion about globalization and being able to ship these things, but there's also an incredible aspect of, say, like a terroir with your work, right? That it's a Chardonnay or that it smells like curry, and there's this amazing sensitivity to the work that I think opens up all sorts of new possibilities. Like the technology is no longer this kind of banal, neutral type of thing. You're starting to expose other senses to it, and even, I think a little bit about, say, Frank Lloyd Wright and the arts and crafts, where everything is designed, the textiles, the furniture, the building, the plateware, everything in the house. And I think you end the lecture in a really incredible way where there's a ring on the table, and the whole building. And so there's this amazing way that the technology has come, or might come full circle as a way to be thinking about these things. So I really want to thank you for joining us here and sharing your work.
Thank you so much. All right, thanks.
My third time.